Hi everyone, and welcome to this example video where we will see an example how we can solve an exact differential equation. So first of all, you can see that I have written down an equation over here, and first thing we want to do is that we want to check whether this equation is an exact differential equation. So let's begin. So step 1, first of all, we need to check whether this equation is exact differential equation or not. To do that, if you recall from your theory lecture, that our p of y, that is partial derivative of p with respect to y, will be equals to q of x, which means partial derivative of q with respect to x. Now, what is p and q over here? First, you need to identify them. So p of xy will be just y square plus 4xy cube plus 2, and q of xy will be 2xy minus 6x square y square, right? So now we want to check whether this condition over here is fulfilled or not. If this is fulfilled, we can try to attempt for a solution. If this is not fulfilled, then we'll say this is not an exact equation. So let's first do dp by dy, that is py, and if you do that, this will be 2y plus 12xy squared plus 0, because 2 is a constant. So let's not write 0 like this, and let's give a partition over here. We have found out p of y. Now to find q of x, so that means dq dx, and if you do that, this will be 2y plus 12xy squared. So you can see that p of y is equals to q of x, right? So this means the equation over here is an exact equation, right? So now our first step is done. So let's go for second step, step 2. Obviously you can write it like this: equation that was given to us is an exact equation. So now step 2. So if you recall from your theory lectures that if you had an exact equation, you can always find a function whose differential d of f of xy is 0, just like the equation itself. And from here, if you expand it in terms of the partial derivatives, you would have something like this: f of x dx, f of y dy, right? And if you had compared them, they would give you that f of x is equals to p, right? And f of y equals to q. Now let's start with this f of x equals to p thing first, because this will help us in getting the function f of xy. So let's try to do that first. So again, our p over here is y square plus 4xy cube plus 2. So let's write that again so that we don't confuse ourselves. So this was y squared minus 4xy cube plus 2. This was p of xy, right? Or just, I'm not writing the f of p of xy explicitly, but you understand this is a function of two variables. So this equation over here, let's call this equation 2, and this is giving us df of dx, sorry, not df, rather partial f of x, which is the partial derivative of f with respect to x, as p, which is equals to y square minus 4xy cube plus 2, right? So now you write df dx is equals to y square minus 4xy cube plus 2. Now you want to integrate both sides. So if you integrate on the left hand side, that is like this: df dx like this, and you have y square minus 4xy cube, sorry, plus 2 dx. Then you will have f of xy. This will be xy squared. Then you will have 4 minus, there is a 4 over in front, and here there will be integration of x dx, so that will give us x squared by 2. So we have 4 times x squared by 2 times y cube, and finally you will have 2x. And if you recall from your theory lecture, since you are integrating with respect to x, and the derivative of f with respect to x will just return this function over here, the constant will be a general function of y, so let's call that g of y. And we need to find out this g of y by using our conditions that we saw in the theory lectures. Other than that, this f of xy is incomplete, right? Some part of it we don't know yet. So again, to write this thing completely with some simplification, will be just minus 2 x squared y cube plus 2x plus g of y, right? Okay, we did something, we made some progress. But now how to find g of y? So step 3 will consist of finding g of y. So if you recall from theory lectures, and as you can see from here, that f of y was equals to q, right? And this will be the condition that will help us finding g of y. So this will help us finding g of y. And the reason I'm selecting this one is because if you take derivative with respect to x from here, let's call this 3. If you take these functions, that is f of f, and you take the derivative with respect to x, this g of y actually goes to 0, right? So we need to take derivative with respect to y, so that g prime of y, or the derivative of g with respect to y, survives, and then we can solve for g of y. So first what we need to do is that we need to do a partial differentiation of f with respect to y. If you do that, this will be just 2xy minus 6x squared y squared. This part will go to 0 because this is just 2x, and finally you will have g prime of y. That means the derivative with respect to y. G prime is just dg dy, or obviously you can, since this is a function of y only, you can write it as dg by dy. So we found this partial derivative of f with respect to y, but this condition fy equals to q will give us something for the left hand side. So our q was 2xy minus 6x squared y squared, right? So let me just write down this whole thing explicitly so it is easy for you to understand. Q was 2xy minus 6x squared y squared, and this is equals to 2xy minus 6x squared y squared plus g prime of y. And we have a very simple equation for g prime of y, because this part and this part will cancel out, this part and this part will cancel out, and we'll have finally g prime of y equals to 0. And if you integrate both sides, you will get g of y as some numerical constant. So let's call that constant c. And now our step 4, we put back g of y into 3, that is equation 3, and we have f of xy as xy squared minus 2x squared y cube, that is xy square minus 2x square y cube plus 2x plus capital C. This is our function that will contain the solution implicitly. That is the solution y of x, because you can see this is a function of both x and y, and this function will generate the solution curves. And obviously, if you notice that in the beginning I gave some initial conditions as well here, that y of 1 is equals to 1. So for a particular solution, that is for a particular value of c, if you want to get that, now you have to use that initial condition, right? So the question now arises is that from where do you use that initial condition? Now, if you recall from our theory lectures and also some portion of this lecture, that this function over here was a total differential, it had a total differential of 0, right? So this function itself can be written as a constant, let's say c prime, and without loss of generality, we can take c prime to be equals to 0. So this is the thing that is going to help us finding this constant c for a particular solution. So if you do that, that is if you put f of xy equals to 0, this will mean xy squared minus 2x squared y cube plus 2x is equals to minus c, and you can just put this minus c as a c1 thing. So this is your solution, and from here you can obviously solve for y and get the true form, the explicit form, but this is the implicit form over here. This is the implicit form of the solution. So let's now use our initial conditions, that is y of 1 equals to 1, that is given over here. So when y of 1 equals to 1, this means x equals to 1 and y equals to 1, right? Both of them are 1. So this is just 1 minus 2 plus 2 equals to c1, and this will be just c1 equals to 1. Now put that back over here, and finally our solution in the implicit form is xy square minus 2x square y plus 2x is equals to 1. And the same solution can be obtained if we had started with this guy, f of y equals to q. Then you would have to integrate q with respect to y. Then you would have to find some h of x. To do that, you would need to take the derivative of that f of xy with respect to x, then equate it just like we did here, and finally you would have to take f of xy to be 0. That is the thing we did over here because of this condition that df is 0. And after doing all that, in the same process as we did here, you would end up with the same solution, that is this one. So this is how if an equation you are dealing with is exact, can be solved, but the solutions will most of the time come in a format of this, like this. That is, you will not be able to explicitly solve it, but you can do that, but that's not necessary. For exact equation, if you have a form like this, that is enough. So what we want to say to conclude is that if you have an exact equation, you don't need to focus on what is y, rather you need to focus on what is f of xy, the function that will generate the solution curves. So this will be it for today, and I'll see you guys on the next lecture. Thank you.